Acha, okay. So this is the recording of the third, I think, tutorial that got corrupted. So this will be a recap, basically the entire tutorial that was missed. So first, let's understand the problem statement. The problem statement is that there is an array of size n, and we would like to find the lower bound on the number of comparisons to sort it. Now, as was previously discussed in class with Sir Gibran, you guys probably know this value to be in the order of n log n, and I might make a tutorial, like a short video on explanation for this. But for now, we'll just move along with the assumption that it was n log n. Okay. Now, what are we doing different in this tutorial? Well, the array is still of size n. However, there are a lot of duplicates, such that the number of unique elements is actually bounded by log n. So there's a lot of repetitions. So and what you would like to see is कि अच्छा अगर इतने amount of unique elements हैं where the number of unique elements is O of log n. Now what is the lower bound on the number of comparisons you would require for sorting this? Now you start off with representing the number of unique elements as k. So we're going to call the number of unique elements as k. Now let's first understand how many, how we're actually going to move along with this proof. Now in the original problem where the array was of size n and there were n unique elements, the idea was that we found how many permutations we could make out of n elements, and that came out to be n factorial. Because it's पहले डब्बे में n आती हैं, अगले में n minus 1, so on and so forth until n times, all the way down to 1. And so that came out to be n factorial. And these were essentially the possible permutations that you could choose the sorted outer order from. And exactly one of these was the sorted array. Now, when we're considering repetitions, since there are n elements in our array, we still have n n factorial permutations. However, we also have repetitions within them. Now, first, let's understand how many repetitions you would see given that there were k unique values. So, if you had an array of let's say size 5, okay, and you had 2 2 and then you had 3 3 3 and 3, you could rearrange this in the form such that you actually swapped these two twos, right? So if you think about it, actually no, let's take another array. This is going to be hard to understand. Let's say our array was something like this: 2 3 2 3 and 3, right? Now this is exactly one permutation of this array. Another permutation of this exact array could have been if we had switched around this guy and this 3, right? Then it would be 3 2 2 3 and 3. Let's say, for example, instead of that, we had switched around these two. Now, essentially, this is another permutation in which, now this is another permutation जिसके अंदर 2 यहाँ पर है, यहाँ पर भी 2 है. Essentially, I've swapped these two elements, but they look the same, obviously, because they're both 2's. और दरमियान में 3 3 3 है. This is a distinct permutation, but it looks the exact same because it's a repetition, right? If I considered all these permutations with the repetitions, then I would come out to be n factorial, which is exactly 5 factorial in this case because n is equal to 5. However, we would like to see how many repetitions we actually have. So let's start counting the repetitions of this exact array. How many copies of this array can we make which are actually, distinct permutations? Well, you could have swapped the twos, एक या तो 2 2 होगा या 2 2 होगा, the two positions for the twos are there are two positions for them. Now these threes, let's call them A, B and C वाला 3, ठीक है? Now इनको इन्हीं डब्बों में आना तो है, इसी जगह पे आएगा, इसी जगह पे आएगा, इसी जगह पे आएगा. ना हो सकता है ये ए बी सी हो, या हो सकता है ये बी ए सी हो, या सी ए बी हो, all the different ways that you would order three elements. So if you actually wanted to order A, B, C wale threes, you could actually put three possible here, then two here, then one here. Basically this classic permutation. If I have um, uh, k copies of the elements, and there are k spots to fill them in, then the number of ways I could have arranged those, the same valued element would actually be, k factorial. In this case, uh, sorry, it's a little intuitive. इसको मैं बना देता हूँ 5. If this was 5, then this would look like, there's 3 factorial ways to arrange these fives. ये जो in positions पे हैं, because यहाँ पे 3 ways, यहाँ पे 2 ways, यहाँ पे 1 way. So for each element, if there are k copies of that element, then there are k factorial ways to arrange those elements in its place, right? In each of those forms of repetition, or in those के लिए भी, in twos के लिए भी, there's going to be, because there's 2 copies, it's going to be 2 factorial ways. So for any given permutation, now we have the formula. For any given permutation, there are exactly, for this, in this case, it's going to be 2 factorial multiplied by 3 factorial ways to arrange this. In general, if I had k unique elements, where ni is the number of repetitions of the ith unique element, then I can actually write my I can actually write my entire repetition for any. So if I have any given permutation in my array of size n, जिसके अंदर k unique values हैं, जहाँ every unique element, the ith unique element has ni repetitions, then the number of repetitions for any given permutation would actually be uh, n1 factorial multiplied by n2 factorial multiplied by n3 factorial, ठीक है, and so on and so forth, all the way up till nk factorial. This is basically saying कि अच्छा, let's say the unique elements were 2 3 5 7, right? 2 3 5 7, 2 3 5 and 7, and there was, let's say, 4 copies of this, then there were 6 copies of this, 8 copies of this, 10 copies of this. Then the ways to arrange this would be actually 4 factorial multiplied by 6 factorial multiplied by 8 factorial multiplied by 10 factorial, and so on and so forth. You get the idea. Now, this tells us exactly how many permutations we have. We can rewrite this as, summation वाला notation. Summation में हम क्या करते थे, इस तरह iterate करते थे, you would sum over the values. यहाँ पर हम क्या करेंगे, यहाँ पर हम pi वाला notation करेंगे, which is the exact same thing, but you're multiplying the values of the function. In this case, I would start at 1, it would go up till k, and you want to be multiplying ni factorial. So this is basically for I till k, multiply all of the values of ni factorial. So n1 factorial, 2 factorial, 3 factorial, so on and so forth, all the way up till nk factorial. So this tells us that any given permutation in our, हमारे पास total permutations, if I have an n size array, even if it has repetitions, is n factorial. And for any given permutation, we have exactly this many repetitions of that permutation. अब फर्ज कर लीजिए हमारे पास n factorial को एक साइड पे कर देते हैं. Let's say the total permutations is equal to, let's say it's 25,000, and there's exactly 25 copies. Let's say I say there's exactly 25 copies or repetitions of any given array, because there's copies of them. So total permutations अगर मैं n factorial लेता, ये this is a imaginary value. Let's say the total permutations is 25,000, and I tell you कि हर permutation के 25 copies हैं. So if I ask you then कि यार unique values कितनी हैं, तो तुम कहोगे यार simply 25,000 लो. This is the total permutations. Every permutation has 25 copies, so this tells me there's exactly 1,000 unique permutations. इसलिए हर permutation की 25 copies हैं, repetitions हैं. That's why I have a total of 25,000 permutations. So this is fairly simple. What does this tell us? Well, this tells us exactly how many unique permutations we have. The number of unique permutations thus would be, आप सारी permutations निकालो, sorry, तो सारी permutations n factorial, तो you just divide that by the copies. So I is equal to 1 till k ni factorial. This is the number of repetitions of any given permutation. What you'd like to do now is you would like to find out, acha, this is the amount of unique permutations of our array. Exactly one of these is sorted. अब sorted वाले के अंदर, let's say अगर हमारा array था उसमें copies थे, तो 1 1 1 2 2 3 3 3 4 4 4 इस तरह. This is a sorted order. Now there's going to be exactly one permutation with this sorted order. पहले क्या था, when we were considering all n factorial permutations, there were actually this many copies of the sorted array. right? So now that we know that the unique number of permutations is this, we know that exactly one of these is our sorted permutation. Or agar aapko yaad ho from the the proof for the lower bound on an n size n unique element array, it came out to be n log n, and that was essentially आपके पास एक adversary था या जिस तरह भी आप समझते हैं, and the leaves were the unique permutations, and exactly one of them was your sorted array, and you made your way down the tree times two times two times. There was a choice of compare. Whenever you made a comparison, there was a comparison between two elements A and B, and you had two choices in tree, and so on and so forth. You got down to the bottom of the tree, and after so many evaluations, you got down to the bottom, and the evaluations got down to the leaves, where the leaves were of number n factorial. In this case, now the leaves will be of number this. There are that many leaves because the number of unique permutations is this much. So this is how many leaves we have. Now we're starting from a root and we're making our way down, all the way down up till we get this many leaves. So we'd like to know how many comparisons we made in the worst case to get down to the bottom of the tree. And so you just, इस पे log लगा दो to find the depth of this tree. तो हमारे पास लीव्स इतने थे, हमने रूट से शुरू किया ऑल द वे डाउन. वी वुड लाइक टू फाइंड आउट हमारे ट्री की डेप्थ कितनी है. अगर लीव्स हमारे इतने हैं तो हमारी डेप्थ होगी दिस इस पर लॉग. ठीक है. नाउ वन मोर थिंग टू डेमोन्स्ट्रेट हियर इज दैट since we're finding the lower bound on this, so we're going to consider the worst case. कि कम से कम अगर बुरा से बुरा भी हुआ हमारा case, you would actually be you would have to do at least this much work, right? So the lower bound would require us to maximize this value. Sorry, the lower bound would require us to maximize, sorry, not this entire value. We just want to maximize the number of leaves we have, right? Because that's going to get us the maximum amount of comparisons we actually have to at least make. So to make this value as high as possible, देखो ये तो बदलेगा नहीं because we have an n-sided array. This is actually variable because we have said that there are k unique elements, but हो सकता है किसी के दो हों, किसी के चार हों, किसी के पाँच हो, छः. लेट्स से अगर हमारे पास 100 एलिमेंट्स थे, हमारे पास सबके 10 10 10 10 कर देते, 10 10 10. If we had 100 total elements and 10 unique elements, one way to arrange it is सबको 10 10 10 10 दे दिए. Another way to do this is कि पहले 9 elements के 1 copies थे और जो आखिरी element था उसके थे 91 copies. So there are 9 ones and एक element had 91 copies. So if you think about it, how many of these have the most repetitions? If you want to maximize this value, the entire fraction, we would like to minimize the denominator, right? Now, if we want to minimize this denominator, we would like to actually make this value as small as possible, and that would actually require us to equally divide all of the ni's. ni's क्या है? सब सारे जो हमारे वो यूनिक एलिमेंट्स हैं उसके रेपिटेशंस हैं, और हम देखेंगे क्यों है. लेट्स से इफ यू हैड 10 एलिमेंट्स, ठीक है, एंड यू हैड इंस्टेड ऑफ आपने कहा 1 1 1 1, देयर आर 9 वंस, और जो आखिरी एलिमेंट है ना, द 10th एलिमेंट, उसके बना दो सॉरी क्या, अच्छा हाँ, 100 एलिमेंट्स हैं, और हम क्या करेंगे, exactly the same thing as I said before. We have 100 elements and we said कि जो पहले 9 यूनिक एलिमेंट्स हैं ना, उनके 1 कॉपीज हैं. जो आखिरी 10th एलिमेंट है ना, यहाँ पे लिख लेता हूँ, 10 is equal to k, k is the number of unique elements. तो हमारा जो 10th यूनिक एलिमेंट है उसके हैं कॉपीज 99. तो अब क्या होगा कि हमारा फैक्टोरियल, ये जो वैल्यू है ना, दिस इज द मल्टीप्लिकेशन ऑफ ऑल ऑफ दीज फैक्टोरियल्स. तो इसका फैक्टोरियल, इसका फैक्टोरियल, इसका फैक्टोरियल, so on so forth. Now the thing is, factorial is something that grows exponentially. So you'd ideally want one of the values to be really 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 large. ठीक है, हमें डिवाइड तो करना है ही across 10 unique elements, लेकिन if one of the values was very large, then this product could grow very large. If you divide the value across multiple things, तो आप क्या करोगे, फर्ज कर लीजिए इसका एक कम कर लेते हैं और एक में से इसको डाल देते हैं. तो अगर इसको मैंने 98 से 99 से 98 बना दिया, तो इसकी वैल्यू तो अच्छी खासी ड्रॉप करेगी. इट विल डिवाइड बाय 99, राइट? द फैक्टोरियल हैज एक्चुअली बिकम 98 फैक्टोरियल इंस्टेड ऑफ 99 फैक्टोरियल. बट दिस गाय इज एक्चुअली गोना गेट लाइक वन मोर. ठीक है, सो इंस्टेड ऑफ हैविंग वन, नाउ यू हैव टू, or 2 factorial is actually not a lot more than 1 factorial, you notice. So as we divide, so let's say as we spread out this value, the smaller ones का जो increase आता है ना, उनका जो factorial की value का increase है, that is not that much. ठीक है, as opposed to how much you're decreasing over here. So if you wanted to maximize this value, which is the number of repetitions of any given permutation, you would ideally put all of the copies in one element, which makes sense. If you want to maximize the number of repetitions, you want कि यार एक जो element है वो बहुत ज़्यादा repeat हो रहा है. Now, conversely, if you wanted to minimize this value, what you would do is you would equally divide the load. You know, हमारे पास 100 elements हैं, where 10 of them are unique. So you would want कि सब में ना 10 10 10 10 डाल दो. And this actually minimizes the value of our factorial products. So what would that look like? That would basically look like 10 factorial times 10 factorial, so on and so forth. That's martaba. In general, if we want to divide the load across k unique elements, where the number of elements is n, we would like all of them to have a frequency or occurrences n upon k. सबकी occurrences होंगी n upon k, इसलिए सबकी k सारे k elements की n upon k occurrences हैं, इसलिए total elements बनेंगे n, and this would actually minimize our repetitions, where the number of uh, repetitions for any element of the k elements is n upon k. So then our product would, instead of ni factorial, because ni factorial denotes कि अच्छा ni ith element के repetitions कितने हैं. अब तो हमें पता है कितने repetitions हैं. कितने हैं? They are exactly n upon k repetitions, right? So this is the exact value. Now what you could do is you could actually find an expression for the lower bound on this. अब क्या करेंगे, इसके बस log लगा देंगे. We get log of n factorial upon, and this is basically n upon k factorial being multiplied k times. So n upon k factorial, n upon k factorial, and so on and so forth. और ये k दफा होएगा, So you can actually replace this entire product by n upon k factorial to the power k, because all of them had exactly n upon k occurrences और सबको factorial लग रहा था. So that becomes your denominator. So now our expression becomes n factorial upon n divided by k factorial power k. Okay? And this becomes log of n factorial minus log of n upon k factorial to the power k. And this becomes uh, k की power यहाँ पर आ जाएगी. So this leaves us with k log n upon k factorial. I'll just simplify this. This is n upon k whole factorial. Don't confuse this with just k factorial. And now what you're going to do is you're going to use something we call, I believe, Ramanujan's approximation, where we say that this is actually equal to, the approximation claims that log of n factorial is equal to n log of n and minus n plus o of log n, minus n plus o of log n. Okay. And in that case, log of n upon k factorial would be n upon k log of n upon k minus n upon k plus o of log of n upon k, right? Adding these values, we would actually get, अच्छा पहले तो let's consider the fact that this is being multiplied by, this entire expression is being multiplied by a minus k. So this expression actually becomes, इस सबसे multiply करेंगे minus k. So this leaves us with minus n log of n upon k plus n minus k times o of log n upon k. Okay? And this expression remains as it is. We can further simplify this expression. We can write this as minus n log of n plus n log of k, because the log ये divide होता है तो this would have come out to be minus log k, और minus उससे लग गया तो it became plus n log k. And then you have, as before, as above, plus n minus k uh, of O of log n upon k. Let's just ignore that for now. Now let's rewrite this expression, which is log of n factorial. And so we have n log n minus n. We have n log n minus n plus O of log n. ठीक है. And then नीचे वाले ऊपर वाले का term था minus n log n. I'm copying this now. And this leaves us with plus n log k plus n minus k times O of log n upon k, right? And this cancel out, this and this cancel out, so you're only left with O of log n, this guy, and then log k, which means the total runtime is going to be n log k plus O of log n minus k of k multiplied by O of log n upon k, right? So we've essentially gotten our lower bound where you make at least n log k comparisons where k is actually, we know that k is upper bounded by O of log n, so this is actually n log of log n, or we could just write it as n log n. Uh, we can ignore this part for now, as that simply comes out to be, because I think it's because, yeah, this expression is larger. So yeah, no. So yeah, we would take the smallest of these expressions, where the smallest of these expressions is actually n log n, because this guy's greater. So we know that we did at least this much work, which is n log n work. So the minimum number of comparisons, or the asymptotic bound on the minimum number of comparisons, was actually in order of n log n.